Right now, every breath you take is a biosignature. The oxygen, the carbon dioxide, the ratios, none of it should exist in chemical equilibrium. Life holds this atmosphere in permanent tension, and from far enough away, it reads like a signal. 124 light years away, James Webb is reading a signal just like it, on a planet it was never designed to find. Tonight, we'll follow the most expensive telescope humanity ever built, and the molecule it found that no one can explain without using the word life. We'll walk through the planet that shouldn't have what it has, the ocean that shouldn't exist, and the scientists who have spent 2 years trying to prove themselves wrong. We'll sit with the question no press conference dared answer directly, the one that changes everything if the answer turns out to be yes. If this is the kind of night you return to, subscribe. It helps this quiet universe keep growing. Here's what didn't make the headlines. When Niku Madhusudan's team at Cambridge released their findings in September 2023, the molecule that generated the most attention was dimethyl sulfide. Every science outlet led with it. And that is the right story. But the thing that shifted the scientific conversation in a more fundamental way was something quieter. Carbon dioxide and methane simultaneously in the same atmosphere. This sounds unremarkable until you understand what it means physically for a planet to have both. Methane is not a stable molecule. In the presence of ultraviolet radiation, which any star provides, even a dim red one, methane breaks apart. It oxidizes. It converts into other compounds and disappears from the atmosphere within roughly 10 million years, give or take, unless something is actively generating it. 10 million years sounds like a long time. The solar system is 450 times older. In geological terms, 10 million years is the equivalent of a month. Methane left alone without a source does not persist. An atmosphere with methane is an atmosphere with something producing it. Carbon dioxide and methane together, at the concentrations observed in K218b spectrum, create what chemists call a disequilibrium signal. The two molecules at those specific abundances should be reacting with each other. They should be slowly converting. They are not converting. They are held in tension, maintained at concentrations that require ongoing production. On Earth, that maintenance is performed by life. Organisms produce methane. Organisms consume carbon dioxide. The ratio is not random. It is managed by metabolism. The question nobody in the Cambridge analysis could fully answer, the question that remains genuinely open, is whether K218b's disequilibrium has another explanation. Something geological. Some interaction between the star's radiation and the hydrogen-rich atmosphere that produces a false disequilibrium signal. The honest answer is that no such mechanism has been demonstrated to work at the concentrations the data suggests. But the absence of a proven alternative is not proof of biology. That is a critical distinction. The disequilibrium is real. The signal is not noise. The data is archived, publicly available, and has been processed by multiple independent groups using different computational methods, and the signal persists. That persistence is what makes this hard to dismiss. It is also what makes it impossible to confirm from 124 light years. With instruments designed primarily for other purposes, looking at a planet that transits its star for roughly 2 hours every 33 days. Here's what most people completely misunderstand about this result. The chemical signal itself is not the controversy. The controversy is what the signal means. And the answer to that, whether the molecules are being produced by organisms floating in a hydrogen-wrapped ocean or by some abiotic process we haven't yet characterized, is not in the data we currently have. But the disequilibrium is there. In a planetary atmosphere, in the habitable zone of its star. And the simplest known mechanism for maintaining it is life. But here's the part that gets lost. The instrument that found this was not designed to look for it. It was built for something else entirely. How it ended up reading the chemistry of an ocean 124 light-years away is a story that starts with a mirror, a sun shield, and 23 years of engineering that had to work perfectly the first and only time. The James Webb Space Telescope's primary mirror spans 6.5 meters across. It is made of 18 hexagonal segments coated in a thin layer of gold, a few hundred nanometers thick, not chosen for value, but for infrared reflectivity, since gold reflects longer wavelengths of light more efficiently than aluminum or silver. Each segment is made of beryllium, a metal chosen because it is lightweight enough for a space telescope, rigid enough to hold its shape at cryogenic temperatures, and workable with the precision that the optics require. To fit inside the rocket fairing, the mirror folded. 18 segments, hinged and locked, that had to unfold in sequence and lock into alignment with a precision measured in nanometers, the width of a few atoms, once the telescope arrived at its destination. The engineering team ran the deployment sequence over 1,200 times in ground testing. In space, on January 8, 2022, it ran once. Webb orbits at a point called L2, the second Lagrange point, roughly 1.5 million kilometers from Earth, on the side away from the Sun. At L2, the gravitational pulls of Earth and Sun balance in a way that lets Webb maintain a relatively stable orbit with minimal fuel. It is cold there. The instruments Webb uses to detect infrared radiation, heat signatures from distant stars, from planetary atmospheres, from the first galaxies after the Big Bang, must operate below 50 Kelvin, colder than the surface of Pluto. The telescope's sun shield, 5 layers of a reflective material called kapton spread across an area the size of a tennis court, keeps the cold side permanently dark by always facing the sun. That sun shield means Webb can observe only roughly 40% of the sky at any given moment. Certain objects, including some exoplanet candidates, must wait for orbital geometry to bring them into view. Webb carries 4 main instruments. NIRCam, a camera for near-infrared imaging. NIRSpec, a spectrograph that disperses light into its component wavelengths across the near-infrared range. NIRIS, a multi-mode instrument that includes GRISM spectroscopy. MIRI, the mid-infrared instrument, which extends sensitivity to longer wavelengths, where molecular features invisible to the other instruments appear. For exoplanet atmospheres, NIRSpec and MIRI are the primary tools. The telescope was designed to study the first galaxies after the Big Bang, stellar nurseries, gravitational lens systems, the formation of planetary systems, and, almost as an afterthought in the original 1996 proposal, the atmospheres of exoplanets. That afterthought now dominates the conversation. What nobody fully anticipated in 1996 was that by 2021, we would have cataloged thousands of exoplanets with known sizes and orbital periods, dozens of them transiting their stars regularly, and several of them positioned in habitable zones close enough to bright enough stars that their atmospheres were detectable, in principle, with the right instrument. Webb turned out to be that instrument. But here is the problem. Reading an exoplanet atmosphere from 124 light-years away is not like pointing a camera. The signal is not light from the planet. It is the planet's shadow pressed into its star's light for 2 hours every 33 days. And extracting chemistry from a shadow that thin requires a method that most people have never heard of. It's called transmission spectroscopy. A planet crosses in front of its star. The star's light, to reach us, must pass through the thin ring of the planet's atmosphere at the edge of the planet's disk. Different molecules absorb different wavelengths of that light. Water vapor absorbs at specific infrared wavelengths. Carbon dioxide at others. Methane at specific bands still. Dimethyl sulfide, DMS, at others. You compare the starlight during transit with the starlight when the planet is not in the way. You subtract one spectrum from the other. What remains in the difference is the atmosphere's fingerprint, the wavelengths it absorbed, mapped to the molecules that absorb them. The difficulty is the signal. Earth-sized planets dim their host star during transit by roughly 1/100%. The atmospheric signal, a fraction of that transit that contains molecular information, is smaller still. It requires stacking many transits, many hours of observation, and statistical methods that are themselves actively debated. K2-18b is easier than most candidates because it is larger. 2.5 times Earth's width, nearly 9 times Earth's mass. Its transits are deeper, its atmosphere thicker, its atmospheric signal louder relative to the noise. But louder is relative. The dimethyl sulfide feature in the 2023 Madhusudan paper was described as tentative. The statistical confidence sat at approximately 1 sigma, meaning the feature appears with that frequency in roughly 30% of random datasets. 1 sigma is a hint. The discovery threshold in astrophysics is 5 sigma, a level at which the probability that the signal is noise drops below 1 in several million. By 2025, follow-up observations pushed the DMS signal to 3 sigma. The Cambridge team's updated analysis reported a confidence level of approximately 99.7% that the spectral feature is real, not attributable to noise. 3 sigma is the level at which a result becomes difficult to dismiss. The particle physics community uses 5 sigma as the standard for a reason. History is full of 3 sigma signals that evaporated with more data. Here is what 3 sigma actually means in this context. The feature is real enough to take seriously and not real enough to publish as a confirmed detection. It sits precisely in the most uncomfortable territory of science, where dismissal would be premature and where proclamation would be irresponsible. The researchers publishing the result know this. The headlines describing it as 99% chance of life are not quoting the paper. They are translating a statistical confidence in a spectral feature into a probability of biology, a translation that skips several layers of inference and presents as certainty something that is, at its most optimistic, a suggestive pattern in light. The light, though, is genuinely suggestive. And here's the part that keeps the retrieval teams running the analysis again. Dimethyl sulfide does not appear naturally in the spectrum of any proposed non-biological atmospheric process for a planet of K2-18b's composition, at the concentrations the retrieval suggests, under the conditions its star produces. The feature is there. its origin is not. And to understand why dismissing it is harder than it sounds, why the teams that have tried cannot make it go away, you need to go back to the planet itself, not to what it contains, to how unremarkable it was supposed to be. K218b was discovered in 2015 by the Kepler Space Telescope's extended mission. It was catalogued, given a designation, filed. At the time, it was one of roughly 4,000 exoplanet candidates in Kepler's growing dataset, a sub-Neptune orbiting an M-dwarf, of interest to planetary scientists studying orbital mechanics, not particularly high priority for atmospheric characterization. There were larger planets easier to observe. There were targets with better defined properties. K218b sat in the queue. Red dwarf stars, M-dwarfs in the spectral classification system, are the most common type of star in the galaxy. Roughly 70% of all stars are M-dwarfs. They are small, cool, and extremely long-lived. Where the sun will burn for roughly 10 billion years total, an M-dwarf of typical mass can fuse hydrogen for hundreds of billions to trillions of years. In cosmic time, M-dwarfs barely age. K218 star is calm, older, less magnetically active than a young M-dwarf. Its flare rate is relatively low. This matters enormously for any planet in its orbit. K218b sits in what astronomers call the conservative habitable zone, the range of orbital distances where liquid water could persist on a planetary surface, given a reasonable atmosphere. The zone is not fixed. It depends on the star's luminosity, the planet's albedo, the atmospheric composition. For a star as dim as K218, the habitable zone sits much closer than Earth's orbit. K218b completes its year in 33 days. In 2017, Hubble detected water vapor in K218b's atmosphere, the first exoplanet in a habitable zone of any star to show confirmed water vapor. The planet moved up the priority list. In 2023, James Webb looked. What the team found was carbon dioxide, methane, and a spectral feature at the wavelengths associated with dimethyl sulfide. The CO2 and CH4 signals were clear. The DMS feature was tentative, but the combination, the disequilibrium of CO2 and CH4 together in a habitable zone planet with a possible DMS signature, was a combination that nobody had seen before in an exoplanet spectrum. Nobody had been able to see it before. Hubble lacked the wavelength coverage and sensitivity. The generation of ground-based spectrographs available before Webb lacked the precision. The measurement wasn't possible. Webb made it possible. And what was measured in that first deep look at K218b's atmosphere was a chemistry that does not resolve easily into the known non-biological universe. But here's the problem nobody could immediately solve. A measurement that doesn't resolve easily might mean something is missing from the chemistry models. The models for Hycean world atmospheres, hydrogen-dominated, ocean-topped, orbiting M-dwarfs, are new. They were developed in anticipation of Webb's results. They have not been validated against a confirmed example of the thing they're modeling. We have one candidate, and what makes it stranger is this. The category it belongs to, the thing that makes it a plausible home for life at all, didn't have a name until 2 years before Webb looked at it. The category did not exist as a named class before 2021. Madhusudan's group at Cambridge proposed it, a class of planet large enough to retain a thick hydrogen-rich atmosphere, but with a temperature and pressure profile that allows liquid water to exist at some depth, either as a surface ocean beneath the hydrogen sky or as a layer within the atmosphere itself. Not a gas giant, not a rocky terrestrial planet, something in between, with different chemistry than either and different habitability criteria than both. The word is a compression. Hydrogen. Ocean. Hycean. The significance is this. Before the category existed, the search for habitable exoplanets focused overwhelmingly on Earth analogs. Rocky planets, roughly Earth's size, with nitrogen-oxygen atmospheres in habitable zones around sun-like stars. The reasoning was straightforward. Earth is our only example of a life-bearing planet, so Earth is the template. The search space was defined by what we already knew. But life, as best we understand it biochemically, requires liquid water, a stable energy source, and a medium for organic chemistry. If these conditions can exist beneath a hydrogen sky, on a planet twice Earth's width, orbiting a red star in 33 days, then the map of where life might be possible is much larger than the Earth analog search implied. There are many more sub-Neptunes than Earth-sized planets in classical habitable zones. The galaxy may have orders of magnitude more Hycean candidates than it has Earth-like candidates. If life can inhabit a Hycean world, the number of potential life-bearing locations in the Milky Way increases dramatically. The model is contested. Some research groups argue that the hydrogen atmosphere, while insulating, would allow ultraviolet radiation to penetrate to the ocean surface and sterilize it. Others argue that the hydrogen itself might be metabolizable. Certain Earth bacteria survive in hydrogen-rich, oxygen-free environments, using it as an energy source. The photochemistry of a hydrogen atmosphere irradiated by a red dwarf produces compounds different from what ultraviolet does to a nitrogen-oxygen atmosphere. The consequences for any ocean beneath are not yet fully modeled. K2-18b is a Hycean candidate. Whether it is a confirmed Hycean world, whether it truly has an ocean, whether the ocean's temperature and pressure allow for stable water, remains a model-dependent inference, not a measured fact. The mass and radius of the planet constrain its interior, and those constraints are more consistent with a water-rich interior than with a gas dwarf interior. But constraining is not confirming. And dimethyl sulfide, if it is present, is on Earth produced almost exclusively by marine phytoplankton, single-celled organisms that float in ocean surface layers and generate DMS as a metabolic byproduct that off-gasses into the atmosphere. If K2-18b has an ocean, and if something is in that ocean, and if that something produces DMS the way Earth organisms do, then the gas Webb detected is the exhaust of alien metabolism. 3 enormous ifs, each one unsettled. But K2-18b wasn't supposed to be the main event. There was a system that came first, one with more planets, closer planets, more candidates in the habitable zone. The system the entire field spent 6 years preparing to study. Webb looked there first. What it found was not what anyone hoped. Before K2-18b dominated the conversation, the most anticipated JWST exoplanet target was a system 40 light-years away in the constellation Aquarius, TRAPPIST-1. 7 planets orbiting a red dwarf smaller and dimmer than K2-18's star. 3 of those planets in the habitable zone. The innermost 4 closer to their star than Mercury is to the Sun. yet potentially temperate because the star gives off so little heat. The system was discovered in 2016 and generated the kind of excitement that is rare in science. Peer-reviewed papers accompanied by NASA artwork, secondary school curricula rewritten around the possibility, the phrase potentially habitable appearing in news outlets that don't usually cover exoplanet science. Webb looked at TRAPPIST-1b first. The thermal emission data, measuring how much heat the planet radiates on its day side, came back in 2023. TRAPPIST-1b's day side sits at roughly 500 Kelvin. That alone doesn't rule out complexity, but the data showed something specific: almost no heat redistribution between the day side and the night side. A planet with a substantial atmosphere, one thick enough to move heat around, shows thermal redistribution. The day side is cooler than it would be on an airless world. The night side is warmer. TRAPPIST-1b showed none of that. The planet appears to be bare, or nearly bare. Without an atmosphere, whatever water it might once have held evaporated or was stripped away. TRAPPIST-1c followed. The second planet, further out, marginally cooler, marginally more hopeful. The data looks similar. High dayside temperature, minimal redistribution, no evidence of a thick atmosphere. The planet may be a Venus analog without the Venus atmosphere, a rock baking on one side and frozen on the other, with nothing in between. The scientific community absorbed this without drama, but also without comfort. The TRAPPIST-1 planets had been the closest thing to a guaranteed target. 7 planets, 3 in the habitable zone, orbiting a calm red dwarf at a distance where spectroscopy was feasible. If any system was going to give early results, TRAPPIST-1 was favored to. What the results for B and C suggest is that proximity to even a relatively calm M-dwarf may be more damaging to atmospheres than the models predicted. Young M-dwarfs are violently active. Even in their older, quieter states, the accumulated radiation history of billions of years may leave the inner planets stripped and silent. Webb is still observing the outer planets, D, E, F, G, where conditions may differ. The results for B and C are not a conclusion for the system. They are a complication. The excitement that built around TRAPPIST-1 between 2016 and Webb's first results was not wrong in its premise. The system is still extraordinary. The data for the inner planets is simply what it is. And what it is for the 2 planets most accessible to Webb's instruments is no atmosphere we can currently detect. The question didn't die. It moved. But it moved carrying a warning that TRAPPIST-1 made unavoidable. Positive results in this field, signals that look like findings, have a history worth knowing before deciding what K218b's chemistry means. The history of biosignature detection is in part a history of signals that didn't hold. In 2020, a team announced the detection of phosphine in Venus's atmosphere. Phosphine is a molecule associated on Earth with biological processes and with very little else in planetary chemistry. The detection was made using the James Clerk Maxwell Telescope and the ALMA array, 2 of the most powerful radio and submillimeter observatories on Earth. The team was credible. The result was peer-reviewed. The signal was real. Within months, other teams had reanalyzed the data. Some found that what appeared to be phosphine might be sulfur dioxide at a frequency adjacent to the phosphine absorption band. The calibration pipeline used for one of the instruments had a known artifact at the relevant wavelengths. Follow-up observations could not confirm the original signal strength. The phosphine claim has never been fully confirmed. It has not been retracted. It sits in the literature, contested, unresolved, a case study in how a real signal in a real data set can resist definitive interpretation for years. Dimethyl sulfide faces a structural version of the same problem. Abiotic DMS, DMS produced by chemistry alone, without organisms, can form through specific interactions between methyl compounds and sulfur under ultraviolet radiation. The conditions required are unusual on Earth. On a Hycean world, where the atmospheric chemistry is hydrogen-dominated and the ultraviolet environment from the host star is different in character from what Earth receives, those conditions may be more accessible than current models suggest. The Cambridge team acknowledges this. Their 2023 paper includes a section on abiotic DMS pathways. They model several and find that none of them, given the available constraints on K218b's atmospheric conditions, produces DMS at the concentrations the retrieval suggests. But we modeled the known pathways and found them insufficient is not the same as the unknown pathways don't exist. Abiotic chemistry is not fully cataloged, especially for atmospheric conditions that have no analog in our solar system. There is a deeper difficulty. The spectrum of K218b is extracted from data in which the planet's transit reduces the combined star plus planet light by a tiny fraction of a percent. The atmospheric signal within that transit is a fraction of that fraction. The DMS signal within the atmospheric spectrum is a fraction of that. At each level of extraction, there are computational assumptions about the star's own spectrum, the planet's pressure-temperature profile, the mixing ratios of molecules already identified, and whether those known molecules might contribute to spectral features being attributed to DMS. Different retrieval methods, different ways of fitting models to the same raw data, produce different results. This is not fraud. It is the intrinsic difficulty of inverting a spectrum into composition when the composition is not fully known in advance. The DMS signal may be real. It may be an artifact of retrieval methods not yet mature enough for this particular class of planet. It may be real as a spectral feature and wrong as a molecular identification. We don't know. And there is no clean path from here to knowing, not with any instrument currently operating. But here's what almost nobody mentions in the coverage of this result. The telescope that made this measurement was almost never built. And the reason it exists at all is a story of 23 years of engineering that had to be right the first and only time. Here's something that took decades to figure out. The James Webb Space Telescope was formally proposed in 1996 in a report titled HST and Beyond, prepared by a committee led by astronomer Garth Illingworth. The original concept called for an 8-meter mirror, a launch in 2007, and a budget of $500 million. The telescope that lifted off on Christmas Day 2021 had a 6.5-meter mirror. The design was revised downward to enable folding within the rocket, a launch date delayed by 14 years, and a final cost of approximately $10 billion. The delays were not failures of will. They were the price of building something with no precedent. Hubble's primary mirror, famously, was polished incorrectly. The error was tiny. The mirror's curvature was off by about 2.2 micrometers, about a 50th of the width of a human hair, but the consequence was spherical aberration that made Hubble's first images useless. astronauts flew up and corrected it. Servicing missions performed over Hubble's life have replaced cameras, gyroscopes, batteries, fine guidance sensors, and solar arrays. Hubble could be repaired because it orbits at an altitude accessible to the space shuttle. Webb orbits at L2. No crewed vehicle currently in service can reach L2. Whatever flaw would appear in Webb's optics or instruments after launch would be permanent. The mirror alignment had to work. The sun shield had to deploy. The secondary mirror had to extend on its tripod arm without contaminating the optical path. Each of the 18 mirror segments had to actuate to its correct position and hold it against the thermal environment of deep space. The deployment took approximately 2 weeks from launch. Every hinge, every latch, every actuator, every layer of Kapton. The engineering teams at Northrop Grumman, Ball Aerospace, NASA Goddard, and the Space Telescope Science Institute had been living with those steps for years. John Mather, Webb's senior project scientist and a Nobel laureate in physics for his work on the cosmic microwave background, watched the deployment on screens in Baltimore. He has said that in the weeks before launch, he didn't let himself think about what would happen if it worked. Only what would happen if specific things failed, and whether the contingency plans were adequate. Nothing failed. The mirror segments aligned. The sun shield deployed. The instruments cooled to their operating temperatures. Webb's first images, released to the public in July 2022, showed galaxy clusters at distances that no prior telescope had resolved at those wavelengths, star-forming nebulae in resolutions that looked almost fabricated in their clarity. A spectrum of exoplanet WASP-39b, showing the first unambiguous detection of carbon dioxide in an exoplanet atmosphere. All of it within the first 7 months of operation. The teams who built Webb over 23 years had built something that performed beyond what the specifications required. That margin, the gap between designed capability and actual capability, is what made the K218b result possible. Webb could read that spectrum. And what that spectrum said, the specific number that came out of the analysis, is the thing that every headline translated in exactly the same way and got wrong in exactly the same way. The phrase 99% chance of life does not appear in any scientific paper about K218b. What the updated Cambridge analysis published in 2025 reports is a confidence level of approximately 99.7% that the spectral feature they observe is not attributable to random noise. This is a statistical statement about the quality of the signal, not a probability estimate for the presence of biology. The distinction is not pedantic. It is the difference between we are very confident that something is producing a pattern in this light, and we are very confident that the something producing the pattern is alive. 3 sigma is the level at which a result becomes publishable and worth taking seriously. It is also the level at which, historically, results have sometimes evaporated with more data. In the physics of the early 2000s, several putative particle detections sat at 3 to 4 sigma for years before additional data resolved them, some into confirmed discoveries, some into statistical fluctuations. The 5 sigma threshold that particle physics adopted exists precisely because 3 sigma signals have a documented history of not surviving. For the K218b DMS signal specifically, the feature is present in the data after multiple independent retrieval analyses using different modeling assumptions. It doesn't disappear when different teams process the same observations. It weakens in some analyses, strengthens in others, but doesn't vanish. This persistence across methodologies is meaningful. It suggests the feature is in the data, not in the analysis choices. What the feature maps to, which molecule or combination of molecules is producing it, requires retrieval models precise enough to distinguish DMS from other molecules with overlapping features at those wavelengths. At the wavelength range relevant to DMS in Webb's NIR spec instrument, several molecules produce overlapping absorption. Separating them requires assumptions about the planet's temperature structure, cloud deck, and the abundances of other molecules already detected. The models are not perfect. They are the best available for this class of planet, which is a class that was first observationally defined by the K218b result itself. 3 sigma, a real feature, an uncertain identity, a biological interpretation that has no proven abiotic alternative. They are running the retrieval again, waiting for the piece that resolves it. But before that piece can mean anything, there is a prior question the press coverage skipped entirely: whether a hydrogen-wrapped ocean can support life at all. And answering that requires reconsidering what the word habitable has ever actually meant. We tend to imagine habitable as meaning familiar. Blue water under open sky, temperatures between freezing and boiling, sunlight reaching the surface. The ocean, as we know it, sunlit, temperate, photosynthetic. But the ocean Earth has presented us with, on close examination, is not one ocean. It is several, layered by depth, separated by thermal gradients and pressure differentials, each with its own chemistry and its own biology. Sunlight penetrates roughly 200 meters before fading to levels too dim for photosynthesis. Below that depth, in regions called the dysphotic and aphotic zones, life continues. It does not photosynthesize. It does not need to. It feeds on organic material drifting down from the sunlit layer above, or it draws energy from an entirely different source. In February 1977, the deep-sea submersible Alvin descended to 2,500 meters in the Pacific Ocean near the Galapagos Rift. The crew expected to find the deep-sea floor as it had always been described: cold, dark, merely barren. What they found instead was a hydrothermal vent system, fissures in the seafloor where water heated by volcanic activity below erupts at temperatures exceeding 400 degrees Celsius, carrying dissolved minerals and sulfur compounds into the surrounding water. And around those vents, life. Tube worms 2 meters long, clams, shrimp, crabs, complete ecosystems organized around chemosynthesis rather than photosynthesis, organisms extracting energy from the chemical reactions between the vent water and the surrounding ocean, with no sunlight involved at any point in the food chain. The discovery did not just add a new type of ecosystem to the biological catalog. It removed what had seemed like a boundary condition. Life, it turned out, did not require sunlight. It required chemistry and energy. The chemistry could be sulfur. The energy could be geothermal. A Hycean world's ocean beneath a hydrogen atmosphere at pressures far exceeding anything in Earth's deep ocean, at temperatures that might range from near freezing to hundreds of degrees Celsius depending on depth, is not an obvious habitat for life by Earth standards. but Earth's own standards turned out to be too narrow. The hydrothermal vent discovery was the first of many systematic expansions of what biologists call the habitable envelope. Antarctic ice sheets harbor microbial communities. Hyperacidic volcanic lakes at pH levels that dissolve iron host organisms called acidophiles. The cooling water of active nuclear reactors has been found to contain radiation-resistant bacteria. The upper stratosphere carries living bacterial spores on dust particles. K218b's ocean, if it exists, is extreme by any measure. But extreme and uninhabitable have never meant the same thing. Every time the boundary was drawn, life had already crossed it. The problem is different. Surviving in a hydrogen ocean is one thing. Being detectable from 124 light-years away is another. And the distance between those two things is where the real difficulty lives. To confirm that K218b's DMS signal is biological and not instrumental artifact or abiotic chemistry, astronomers would need several things they currently do not have. The first is corroborating molecules. On Earth, organisms that produce dimethyl sulfide also generate related compounds as metabolic byproducts: dimethyl disulfide, isoprene, methyl mercaptan, various short-chain organic acids. If Webb's spectrum of K218b were to show a pattern of co-occurring biosignature molecules, not just DMS in isolation, but the broader chemical signature of metabolism, the biological interpretation would strengthen considerably. A single molecule can have multiple origins. A coordinated pattern of molecules associated with specific biochemistry is harder to explain without biology. The 2025 Cambridge analysis tentatively reported an additional signal consistent with dimethyl disulfide, DMDS, at 2 sigma confidence. Too weak to claim. Too consistent with the DMS result to ignore. The second requirement is independent confirmation from a different instrument. The current dataset comes primarily from Webb's NIR-SPEC spectrograph, which observes in the near-infrared range. MIRI, the mid-infrared instrument, accesses longer wavelengths where different molecular features appear. Wavelengths at which DMS and related molecules have additional absorption bands not visible to NIR-SPEC. If MIRI observations show a spectrum consistent with the NIR-SPEC retrieval, the single instrument uncertainty decreases substantially. MIRI observations of K218b are in progress. The third requirement is more transits. Each transit provides roughly 2 hours of atmospheric data. Stacking transits improves the signal-to-noise ratio in proportion to the square root of the number of observations, which means you need 4 times as many transits to double the precision. Pushing from 3 sigma to 5 sigma on the DMS signal, assuming the signal is real and stable, likely requires observations through 2027 or beyond. The fourth requirement is theoretical: a retrieval model specific enough to K218b's atmospheric conditions to reliably separate DMS from other molecules with overlapping spectral features. Those models are being developed. They are not complete. But here's the question that sits beneath all of these requirements. Even at 5 sigma, the signal would confirm the presence of a molecule. Moving from DMS is unambiguously present at high confidence to DMS was made by biology requires ruling out every abiotic pathway that might produce it in Hisian conditions, and those pathways are still being theoretically explored. The answer to is there life on K218b may not be answerable with any instrument currently operating or any instrument currently being built. It may require the Habitable Worlds Observatory, a proposed successor to Webb, still in early design, not expected to launch before the late 2030s, or a direct imaging mission capable of resolving the planet's atmosphere with greater sensitivity across a wider wavelength range. The path from suggestive signal to confirmed biology is longer than any headline suggested. But while the DMS question stays open, the same spectrum is saying something else, something that doesn't require biology to be true, and that most coverage missed entirely. WASP 39b is a hot Jupiter, a gas giant roughly Saturn's mass, orbiting its star in 4 days at a distance so close that its surface temperature exceeds 900 Kelvin. It is not a habitability candidate. It was never described as one. In July 2022, Webb detected carbon dioxide in WASP 39b's atmosphere. Clean, unambiguous, multiple sigma. The first CO2 detection in an exoplanet atmosphere in history. The significance was methodological. CO2 has relatively weak features at wavelengths accessible to Hubble. Webb's infrared sensitivity made the detection straightforward, validating that the instrument could do what its designers promised. WASP 39b was proof of concept. K2-18b followed. The CO2 and methane signals in K2-18b's spectrum use the same instruments and calibration approaches, applied now to a planet in the habitable zone. The transition from proof of concept to science with implications happened within 18 months of Webb's first light. Carbon dioxide in K2-18b matters for a reason beyond the disequilibrium signal. CO2 abundance constrains a planet's interior model. Specifically, it constrains the carbon-to-oxygen ratio, a number that behaves differently depending on whether the planet's bulk composition is mostly rock, mostly gas, or mostly water. A planet with a deep ocean beneath a hydrogen atmosphere will have a different CO2 abundance in its atmosphere than a gas dwarf without an ocean, because the ocean absorbs and releases CO2 differently than bare rock or gas does. The K2-18b CO2 abundance in the Madhusudan team's retrieval is more consistent with a water-rich interior than with a dry gas dwarf interior. Not proof of an ocean, the inference depends on models of carbon-oxygen chemistry in interiors we cannot directly observe. But the spectrum is pointing in the direction of water. At several independent wavelengths, through several independent analysis teams, the spectrum points the same direction. This is the part that is actually most scientifically interesting, and it is the part that gets the least coverage. A planet where multiple independent spectral features, CO2 abundance, CH4 abundance, the possible DMS feature, all point toward the same model of a water-rich Hycean world, is a planet that is being very consistent in what it's telling us, even if what it's telling us is not yet interpretable with certainty. Consistency across independent lines of evidence is not confirmation, but something in the data, independent of DMS, independent of biology, is pointing toward an ocean. And that ocean, if it exists, has a history that the data cannot touch. Billions of years under a star that in its youth was trying to destroy it. Red dwarf stars are the universe's endurance athletes. They burn slowly, at low temperatures, fusing hydrogen over timescales that dwarf the current age of the universe. An M-dwarf of typical mass will be fusing hydrogen long after the sun has expanded, engulfed Earth, exhausted its fuel, and cooled to a white dwarf. In terms of stellar lifespan, M dwarfs are essentially permanent on any time scale that matters to human civilization. But youth is violent. Young M dwarfs are magnetically hyperactive. They emit X-ray and ultraviolet radiation at levels that make the young sun look mild. They flare, sudden massive releases of magnetic energy that can briefly increase the star's luminosity by factors of 10 or more, flooding nearby planets with radiation. For a planet in the habitable zone of an M dwarf, which must orbit close enough that the orbital period is measured in weeks, those flares are not distant events. They are direct exposures. The cumulative effect over hundreds of millions of years of the star's active youth can strip a planet's atmosphere down to bare rock. Mars, at a comfortable distance from a G-type star far less active than any M dwarf, lost most of its atmosphere over several billion years, partly through solar-wind interaction. The stripping rate for a close-orbiting planet around the young M dwarf is substantially more aggressive. K2-18 star is old enough to have calmed. Its flare rate is low by M dwarf standards. The planet's current radiation environment is much gentler than what it would have experienced in the first billion years of the system's history. If life exists on K2-18b, it emerged or survived through an era of radiation exposure that we cannot easily model. Some research groups suggest that a thick hydrogen atmosphere might provide protection. Hydrogen absorbs UV efficiently, shielding the ocean surface beneath. Others argue that the same UV converts the hydrogen into other species that are themselves damaging. The debate is not settled. What the radiation history means is this: any organism in K2-18b's ocean today has either been there through the violent phase, which requires radiation tolerance we haven't characterized for life in a hydrogen ocean environment, or it emerged after the star calmed, which requires that the chemical conditions for life's origin persisted through a long hostile period and then generated life afterward. Both scenarios are possible. Neither is simple. The universe doesn't offer simple scenarios at this scale. It offers ones that require patience, billions of years of patience, and conditions stable enough across that timescale for chemistry to become biology. We don't know if those conditions held at K2-18b. Something was producing a chemical that nothing abionic has been fully proven to produce in the quantities the data suggests. The person who found that chemical, and who spent 2 years systematically trying to make it disappear, built the theoretical framework for detecting exactly this kind of signal before any instrument capable of looking for it existed. Niku Madhusudan joined the Institute of Astronomy at Cambridge in 2012. His early research focused on a specific problem. Given that we would soon have instruments capable of reading exoplanet atmospheres in detail, what would a Hycean world spectrum look like? What molecular features would it show? What retrieval methods would be needed to distinguish a Hycean atmosphere from a gas dwarf atmosphere from a rocky planet with a secondary atmosphere? He built the theoretical framework before the instrument existed to test it. The 2021 paper proposing the Hycean world category was the result of years of work on what would need to be true about a hydrogen ocean planet's atmospheric chemistry for it to be biologically interesting, and critically, for that biology to leave detectable spectral traces. When Webb's NIR spec data for K2-18b came back in mid-2023, Madhusudan's team spent several months in retrieval analysis. The CO2 signal was clear. The methane signal was clear. Both were at confidence levels that justified reporting. Then the retrieval produced the DMS feature. He has said publicly that the team's first reaction was not excitement. It was methodical skepticism. They tested different prior distributions for the atmospheric model. They varied the pressure-temperature profile. They changed the cloud parameterizations. They tested whether known molecules at high abundances could produce a feature that the retrieval was incorrectly attributing to DMS. The feature moved in strength. It didn't disappear. The decision to include it in the paper, labeled tentative, framed carefully, was not a decision to claim a discovery. It was a decision that omitting it would be scientifically irresponsible. If the spectral feature is present at any sigma level and you don't report it, you are selectively presenting your own data. The feature was there. They reported it. What Madhusudan has said he found genuinely difficult in the months after the paper, during the review process and after, was the abiotic modeling. Not the DMS signal itself, but the absence of a clean, non-biological model that accounts for it at the concentrations the retrieval suggests. The known abiotic pathways for DMS production are insufficient. Not zero. Insufficient. The most parsimonious explanation, he said in one interview, is life. We are not comfortable claiming the most parsimonious explanation without eliminating the alternatives. By 2025, the alternatives had not been eliminated. The signal had strengthened, and the follow-up retrieval, 3 sigma, with a possible DMDS companion feature, put the result in territory where it cannot be dismissed, but cannot be confirmed. This is the scientific frontier, not a press conference. A researcher in Cambridge running the same retrieval with more data, checking whether the feature holds, watching a number that was 1.8 sigma become 2.4 sigma and then 3.1 sigma, and trying to figure out whether that trend will continue to 5, or plateau, or collapse. He doesn't know. And the way the broader community has responded to that uncertainty, what it looks like from outside the field versus what it actually involves on the inside, is where the headline "Scientists are panicking" gets the story entirely wrong. Scientists don't panic. Not in the way the phrase implies. What happens in a field when data produces something the existing frameworks didn't predict is more like a slow, uncomfortable recognition that the models need updating, that the assumptions underlying the models need examining, that the next observation needs to be scheduled quickly and carefully. The panic, if it exists at all, is procedural. In 1967, Jocelyn Bell Burnell was a graduate student at Cambridge, working with her supervisor, Anthony Hewish, on a radio telescope she helped build across a field in rural Cambridgeshire. In August of that year, she noticed a signal in her chart recordings that she later described as a bit of scruff, a repeated radio pulse too regular to be natural interference, and too fast to be a natural astrophysical source she knew of. The pulses came every 1.337 seconds, with a precision that exceeded the best atomic clocks available at the time. Hewish's response, before the analysis was complete, was to mark the signal in the logbook as LGM1, Little Green Men, not because he believed it was a transmission from extraterrestrials, because the signal's regularity had no precedent in known astrophysics. The label was ironic, but the discomfort behind it was real. The data was not fitting the known universe. It turned out to be a rotating neutron star, a pulsar, a class of object that had been theoretically predicted but never observed. The discovery won Hewish the Nobel Prize in 1974. Bell Burnell, controversially, was not included. The K2-18b result creates a structurally similar but much smaller and less resolved version of that discomfort. Not because anyone seriously believes biology is confirmed, because a spectral feature that should be explicable abiotically has so far resisted clean abiotic explanation. The data is not fitting this simple universe. The community's actual response, the one that looks like alarm from inside the field, is multiple independent groups are requesting telescope time. Papers attempting more rigorous abiotic DMS modeling in Heysian conditions are being submitted. The observation proposals for follow-up MIRI data have been submitted and approved. The 2025 result prompted a new round of scheduling requests. The alarm looks like more data, more analysis, more precise language in abstracts, more careful hedging that serves not to minimize the result, but to accurately describe what it is and what it isn't. One researcher, speaking at a conference after the 2025 update, said that the K2-18b result is the first time he told his family what he was working on without immediately following it with a qualifier. Not because he believed confirmation was imminent. Because the thing he was working on had become interesting enough that the qualifier no longer felt like the most important part of the sentence. From inside, it looks like more late nights and more telescope time. And some of that time is being spent not on K2-18b at all, but on planets starting to show the same chemistry, around different stars, analyzed by teams who had no involvement in the original result. K2-18b is not alone on the list. TOI 270d is a sub-Neptune orbiting a red dwarf about 70 light-years from Earth in the southern constellation Pictor, discovered by the TESS satellite in 2019. Radius roughly 2.5 Earth-widths, placing it in the sub-Neptune class. Orbit period of 11 days, at the outer edge of its star's optimistic habitable zone. Webb observations of TOI 270d, processed by 2 independent teams and published in 2024, found carbon dioxide and methane. Simultaneously, in a habitable zone sub-Neptune. No DMS claim was made. But the same disequilibrium structure, CO2 and CH4, coexisting at concentrations that require active production, appeared in a completely different system, around a different star at a different distance, using different observation geometries. The significance of this second data point is easy to miss. If K2-18b were the only sub-Neptune showing atmospheric disequilibrium, it could be anomalous. An unusual planet with unusual chemistry that happens to mimic a biosignature. But finding a similar signal at TOI 270d, processed by teams with no connection to the K2-18b analysis, using different retrieval codes at a different wavelength geometry, means one of 3 things must be true. The disequilibrium is a real feature of this class of planet, arising from chemistry specific to hydrogen-rich atmospheres in habitable zones around M dwarfs. If so, understanding that chemistry, whether biological or abiotic, is a new area of planetary science with significant implications for how we assess habitability. Or there is a systematic error in how spectral retrievals handle sub-Neptune atmospheres, and the disequilibrium signal is an artifact of methods not yet mature enough for this class of planet. If so, finding and correcting that error would affect every sub-Neptune atmospheric retrieval in the Webb archive, a substantial recalibration of results already in the literature. Orhisian worlds with active atmospheric chemistry are more common than the models predicted, and we are looking at a class of planet that regularly produces signatures the current abiological models cannot account for. Any of the three would be important. Any would require years of additional work. None resolves cleanly from the data currently available. Webb has active observation programs targeting at least 3 additional Hycean candidates. The list is growing. And here is what nobody mentions alongside that. Every planet on it competes for the same telescope on the same schedule against everything else Webb was built to observe. Getting an answer is not just a question of wanting one. There is a problem here with no elegant solution. Each transit of K2-18b provides roughly 2.5 hours of atmospheric data. The planet transits approximately 11 times per year. Each transit produces a small increment of signal in the spectrum, an increment that diminishes in proportion to how weak the target feature is. DMS, at the concentrations the retrieval suggests, produces a smaller signal than CO2 or methane. Stacking transits improves precision proportional to the square root of the number of observations. More transits, more precision. Estimates from the Cambridge team suggest that moving from 3 sigma to 5 sigma on the DMS signal, if the signal is real and consistent, would require observations continuing through 2027 at minimum, possibly through 2029, depending on observing conditions and telescope scheduling. Webb has enough fuel reserves that NASA believes it will operate for 20 years or more. The time is technically available, but every hour of Webb's time spent on K2-18b is an hour not spent on the dozens of other science programs that competed for the same telescope allocation. The first galaxies after the Big Bang are waiting. Protoplanetary disks where planets are forming right now are waiting. The cosmic infrared background, the composition of asteroid family members, the atmospheres of ice giants, all waiting. The telescope's schedule is oversubscribed by a factor of roughly 5 or 6. For every hour of approved time, 5 hours of competitive proposals were submitted and not approved. K2-18b receives approved time because the scientific community, through the peer review process, has judged the question important enough to prioritize. That judgment has been consistent across the first 2 rounds of approved observations. Whether it holds into the 3rd and 4th rounds, as the signal strengthens or remains inconclusive, depends on results that don't exist yet. And here is what no additional telescope time resolves. Even at 5 sigma, the DMS signal would confirm the presence of a spectral feature consistent with dimethyl sulfide, not the presence of DMS itself with certainty, not the biological origin of whatever molecule is producing the feature. Moving from confirmed feature to confirmed molecule to confirmed source is a chain of inferences, each with its own uncertainty that the data alone cannot close. The instrument that could close it, a telescope capable of directly imaging K2-18b's atmosphere and resolving its chemistry across a broad enough wavelength range with enough sensitivity to rule out abiotic alternatives, does not exist. The Habitable Worlds Observatory, NASA's next major flagship concept, would be capable of something closer to that. Its earliest possible launch date, given current funding and development timelines, is the mid-2030s. We are holding a question whose answer may not be reachable for a decade. The question is real. The evidence is real. The gap between what we have and what we need to know is real. That gap is where the science lives now. But behind the gap, older than Webb, older than the exoplanet field, there is a question the K218b result has made harder to set aside. One that predates this data by 70 years and that nobody has answered cleanly since. In the summer of 1950, Enrico Fermi was having lunch at Los Alamos with colleagues. The conversation had turned to a recent news story, something about flying saucers, a cartoon in the New Yorker. One thing led to another, and Fermi asked a question that he apparently considered casual, given how large and old the galaxy is, and how widespread the conditions for life seem to be. Where is everybody? The question was never intended as a formal paradox. It wasn't published. Someone remembered it years later. By then, it had accumulated the weight of everything the field hadn't solved in the decades between. The Fermi paradox is not one question. It is a cluster of overlapping puzzles about why a galaxy that appears, by every physical measure we have, to be permissive to life, in terms of chemistry, in terms of energy sources, in terms of the time available, has so far produced no unambiguous evidence of intelligence beyond this one planet. No confirmed signal, no artifact, no modification of observable stellar or planetary environments that requires intelligence to explain. Silence. Everywhere we have looked, with the instrumentation we have had available. The K218b result does not resolve the Fermi paradox. It doesn't touch intelligence. Even the most optimistic interpretation of the DMS signal, that it comes from organisms in a Hycean ocean, places those organisms at a microbial level of complexity. Metabolizing, perhaps, evolving, perhaps, broadcasting a signal recognizable as intentional, certainly not. But the result places the edge of the Fermi problem somewhere new. If sub-Neptune planets with atmospheric disequilibrium are common, and TOI 270d suggests they may be, then the number of locations in the galaxy where the chemistry is doing something biology-like is very large. The silence becomes harder to attribute to simple scarcity of life-adjacent conditions. The universe appears to have life-adjacent chemistry in many places. The silence, if K218b signal is biological, becomes a statement about something other than chemistry, about the gap between microbial life and broadcasting civilization, about the timescales involved, about what happens to intelligence in a universe old enough to have produced it many times. These are questions that the K218b result does not answer and was never positioned to answer. What it does is shift the weight of the Fermi problem from maybe life is chemically difficult toward maybe life is common and intelligence is rarer than chemistry makes it look, or toward explanations we haven't yet articulated. The silence continues. More pressured than it was in 2020, and with no clean resolution in sight. And while the implications settle, the instruments don't stop. The data is still accumulating in an archive that anyone with enough knowledge and the right software can access. As of mid-2026, Webb has produced transit observations for dozens of exoplanet systems. The data archive at the Space Telescope Science Institute is publicly accessible. Raw data, calibrated by the Institute's pipeline, is downloadable by any researcher with the computational resources to work with it. Multiple independent groups have downloaded the K218b observations and run their own retrieval analyses. Results have varied in detail. The DMS signal is stronger in some analyses, weaker in others. But no group has produced a clean null result that eliminates the feature. Retrieval science for sub-Neptune atmospheres is a young discipline. The methods being used in 2026 are substantially more refined than those available in 2023, partly because the K218b result itself revealed gaps in the existing methods. The question of how to handle hydrogen-dominated atmospheres with deep ocean boundaries, how to model the photochemistry at the atmosphere-ocean interface, how to separate the contributions of overlapping spectral features in the NIR spec range. These are open problems being worked actively, with K218b as the primary test case. Webb's MIRI instrument is the next major diagnostic tool for K218b. MIRI observes in the mid-infrared range, roughly 5 to 28 micrometers, where molecules have additional absorption features not visible at NIR spec's shorter wavelengths. At mid-infrared wavelengths, DMS and DMDS have features that are better separated from potential confounding molecules. A strong, consistent MIRI detection of DMS-associated features would increase confidence in the NIR spec retrieval and reduce the alternative molecule ambiguity. MIRI observations of K218b have been approved and are in progress. The results are not yet published. They may arrive within the next year. The result could confirm the DMS feature, or produce a spectrum that makes it disappear, or land somewhere in between, which is the most common outcome in a field where the question is genuinely hard. But whatever MIRI shows, one thing no instrument result changes. The light carrying the answer left K218b before any of us were born. 124 light years. The light that Webb is reading from K218b's atmosphere left that system in roughly 1902. The Wright brothers had not yet flown their first powered flight at Kitty Hawk. That happened in December 1903. Quantum mechanics did not exist as a theory. The electron had been identified, barely. The word galaxy in its modern sense, to describe a star system separate from the Milky Way, had not yet entered scientific vocabulary. The light arriving at Webb's mirrors now, in 2026, left K218b in 1902. Whatever K218b's atmosphere looks like today, whatever its chemistry is doing as of this moment, that light will not arrive here for another 124 years. If there is life on K218b, it has no knowledge that we exist. The chemical signal it sends into its star's light is not intentional. It is metabolic exhaust, the same kind of exhaust that Earth has been leaking into sunlight for 3.5 billion years, without any organism meaning to. The dimethyl sulfide that phytoplankton off-gases into Earth's atmosphere is not a broadcast. It is a byproduct. Life makes DMS the way a candle makes heat, incidentally, as a consequence of doing something else. If K218b's DMS comes from organisms, those organisms have no awareness that a gold-coated mirror 124 light-years away is reading their exhaust. They have no awareness of anything beyond their ocean, their chemistry, their interactions with each other, and with the hydrogen above them. This is the full weight of the observation. We are reading the unintentional signal of organisms, if they exist, that are separated from us by a distance so large that the speed of light, the fastest thing permitted by physics, takes 124 years to cross it. We cannot go there. Not in any timescale human civilization has ever maintained itself. The nearest we could reach K218b with any propulsion system currently conceivable would take tens of thousands of years. The universe handed us a question. It is not inclined to also hand us a straightforward path to the answer. It placed the most suggestive evidence for life beyond Earth at a distance that makes verification through direct inspection practically impossible on any human timescale. What we have is the light. And what the light is saying, as best we can read it, is something here is doing chemistry that nothing abiotic has been fully proven to do at these concentrations, in these conditions. Something here. And the people who spent their careers building the tools that can read it, who were in their 20s when the telescope was first proposed, always knew this moment would arrive before they could be certain what it meant. There is a kind of scientist who enters this field because they want the long problems, not the solvable ones, the ones that outlast careers. The ones where the data accumulates over decades, where the answer arrives not as a press conference, but as a gradual thickening of evidence, where being in the field at all is a choice to live with sustained uncertainty. They chose exoplanet atmospheric science when the field was speculative, when no one had detected an exoplanet atmosphere, when the instruments they needed were being designed, when the questions they wanted to answer couldn't even be framed with the vocabulary available. They chose it knowing the results would not arrive on a timeline that respects a grant cycle or a tenure review. What they did instead was build. They wrote the retrieval codes that everyone now uses. They published the calibration papers that nobody outside the field reads, but that every analysis downstream depends on. They developed the theoretical frameworks for Hycean world chemistry before any Hycean world candidate existed. They spent years not finding life, building the substrate on which someone else might eventually be able to look. Webb itself was built by people who understood they would not live long enough to see its full scientific output. Engineers who joined the project in 1998, who would have been in their late 20s then, have now spent their entire professional careers on a single instrument. They ran the deployment simulations over 1,000 times. They replaced components and redesigned systems, and watched schedules slip and budgets grow, and rebuilt their plans around whatever the funding situation required, year after year, for 23 years. The telescope unfolded in space in January 2022 and performed beyond what its design specifications required. What that margin, the gap between designed capability and actual performance, has given us is a measurement that nobody was completely certain was achievable until it was made. A chemical signal in the atmosphere of a planet 124 light-years away, sitting precisely in the territory between suggestive and confirmed, doing exactly what the most scientifically interesting possible result would do, not answering the question, but making it impossible to walk away from. Madhusudhan has said that whatever the K2-18b result ultimately means, biology, chemistry, artifact, something else, it has permanently changed the question. Before it, could there be life in a Hycean world, was a theoretical question. After it, there is a specific system, a specific planet, a specific spectrum, and a specific chemical feature that requires explanation. The question has a location now, a direction in the sky. That specificity is permanently in the record. One system, one planet, one chemical feature. And one question at the center of all of it that nobody, not the Cambridge team, not the independent retrieval groups, not the theoretical modelers, has been able to answer cleanly. The honest scientist, if you ask what K2-18b spectrum means, will tell you we don't know. Not the false modesty of reflexive scientific hedging, the protective we don't know that researchers add to claims they are actually quite confident about to avoid the embarrassment of being definitively wrong. The genuine, unresolved we don't know. What we have is a maybe that is better supported than any maybe we have held before. That qualification, better supported than any maybe we have held before, is not a small thing. For most of human history, the question of whether life exists elsewhere was purely philosophical. It produced no data. It produced arguments, estimates, the Drake equation's famous string of unquantifiable probabilities, Fermi's lunch question, thousands of years of speculation that could not be advanced by observation because the observations were impossible. Now there is data. Not a conclusion. Not a confirmation. Data. Specific, archived, publicly accessible, actively contested across multiple independent analysis teams, being refined and extended and tested, pointing at a specific location in the sky that any amateur astronomer can find on a clear night with a star chart. The constellation Leo. The area between its two brightest stars, Regulus, the heart of the lion, and Denebola, the tail, contains a faint red star invisible to the naked eye. Around it, every 33 days, a planet crosses in front, and the light that reaches Webb's mirror carries the fingerprint of that planet's atmosphere. That fingerprint contains, at 3 sigma confidence, a feature consistent with a molecule produced on Earth almost exclusively by living organisms. Maybe it is life. Maybe it is an abiotic process not yet characterized in the literature, something specific to hydrogen ocean worlds under M-dwarf irradiation, a gap in the models rather than a gap in the universe's tendency towards simplicity. The honest answer is that we cannot yet distinguish between these possibilities. What has changed is the character of the uncertainty. Before Webb, maybe there's life on a Hycean world was a statement about categories, about whether the class of object could exist and whether the class of chemical environment could support biology. It was structural uncertainty about whether the question was even worth asking. Now the uncertainty is about a specific feature in a specific spectrum from a specific planet. That is a different kind of maybe. A located one. A maybe with a 33-day period, 124 light-year distance, a name, a designation, a Cambridge retrieval code, and a feature that 3 independent analyses have failed to eliminate. We are still reading. The air you breathed at the beginning of this night carries the signature of life, not metaphorically, chemically. In the disequilibrium your biosphere maintains without effort or intention. 124 light-years away, something appears to be doing the same. We've drifted tonight through the cold architecture of a question. From the chemistry in your lungs, life's fingerprint pressed into air without intention, to a telescope unfolding its golden mirror 1.5 million kilometers from Earth. From a planet discovered and catalogued and almost overlooked, to the spectrum that made it impossible to ignore. From the instrument's proof of concept on a planet too hot to interest anyone, to the signal in a habitable world that nobody fully expected to find. The universe has held this light for 124 years, patient the way physics is patient, not because it is waiting for us, but because it has no reason to hurry. The signal leaves K2-18b's atmosphere whether or not anything reads it. We are, as of this particular moment in history, learning to read it. The air in this room is still carrying the same chemistry it carried when you started listening. Methane, carbon dioxide, the trace of DMS from ocean organisms you will never see, held in a disequilibrium that the universe would prefer to resolve into silence. Life, maintaining the tension. Somewhere in Leo, in an ocean that may or may not exist beneath a hydrogen sky, something may be doing the same, holding a chemistry against the physics that would simplify it, metabolizing, without intention, without awareness, leaking exhaust into a star's light, the way Earth has been leaking exhaust into sunlight for 3.5 billion years. We sent a telescope to read it, and the telescope is still there, still cold, still reading. If your eyes feel heavy, let them close. If this felt like home, leave a comment when you wake up. If you're still here, the next chapter is waiting. The universe will still be here when you wake up. So will we. Good night.